In this video, we're going to be factoring quadratic trinomials where the a value is greater than 1. Now, there's a lot to unpack here. I want to be efficient with this, but I also want to be thorough. Some necessary skills would include being able to factor integers, identifying and factoring out a greatest common factor, adding and subtracting with negative numbers, and being able to multiply polynomials. In order to factor quadratic trinomials with this method, multiplying polynomials is probably one of the most important skills to have. So I just want to show you some patterns when you're multiplying, in particular, binomials. So we have this binomial that I've generically named as A and B and C and D. You'll notice I don't even have any symbols in there. They can all be plus signs. It doesn't really matter. They could all be negatives just as the same. But I'm going to be doing A times C, and that will always be the first term of my answer. Since they're in the front, we're just going to keep it in the front for now. And B times D would always be the last term. The factoring that gets tricky is understanding how this multiplication occurs when you're distributing, and that those get multiplied together. And when you're doing a quadratic, okay, that's a second degree, quadratic trinomial, these two will be like terms, and therefore you will combine them. So it looks like we have 4 terms, but after combining these two, you're actually going to have a trinomial. So when we're factoring a polynomial, we're trying to take the trinomial, and we're trying to work ourselves backward to come up with what we call our factors, which would be binomials in those situations. This will make more sense when you start seeing some numbers, but I want you to know how to multiply binomials very efficiently and understand some of the calculations that are made while doing that process. So here we go. Here's our first example. The first thing you should always do is look at your A, B, and C values, and also variables, but see if there's a greatest common factor. I see a 5, 52, and a 63. There is no number other than 1 that goes into those 3 numbers collectively. So there's no GCF, and there's no reason to look to factor 1 out then, because it's just a 1. So because this is a quadratic trinomial, I expect my answer to be 2 binomials being multiplied together. And so from the previous slide, we talked about how this was actually going to be the result of multiplying 2 things together, and they would be right here in my binomials. Luckily, 5 is a prime number. We appreciate prime numbers as opposed to composite numbers because of the lack of factors that it has. The only way that I can multiply to get 5n squared using whole numbers would be 5n and n. So I know that that's part of my puzzle. I know that it's 5n and it's n. Now I'm going to look at the last term, which is the 63. Now there are multiple ways to multiply to achieve a 63. It could be 1 and 63. It could be 3 and 21. It could be 7 and 9. Those are the only 3 options. It is our task to figure out which pair of numbers is going to help me achieve a 52, a 52n. And here's how multiplying polynomials will help you. We're going to imagine that this number is a 1 and that this number is a 63. If I multiply this together, I would get 1n, and I would get 63 times 5, which is a very large number. 315, I think. Now, if I use my skills to understand that this 63 is positive, the only way you can multiply 2 numbers to get a positive is if they're both negative or they're both positive. Since we're trying to find a positive 52, I know both of my signs will be positive here. And I'm trying to add then, because they have the same sign, I'm trying to add 1n with 315n. And I'm not going to get 52 in when I do that. Okay? So I know it's not a 1, and I know it's not a 63. However, because the 5 in and the in are different values, I should actually check the other way around. And I would normally write that down here as well. So it could be 63 and 1, and it could be 21 and 3, and it could be 9 and 7. So I actually have 6 combinations that I should check. Now, this all seems like a lot of work right now, and it is. But you'll get faster at it, and you'll also start to recognize patterns as to what numbers they might be. 63 times 5 already puts me at a very high number, and I can't get 52 out of that. But let's try 3 and 21. Well, 3 times n, so I'm doing 3 here, 3 times n, 21 times 5, that's already over 100. So it's not 3 and 21. So I can start to cross these off. And now let's look at a 7 and a 9. If I put a 7 here, I would get 7 in, and a 9 here, I would do 9 times 5, so 45 in. And if I add those together, I actually do get a 52. So this is my pair of numbers. I already determined that my signs would both be positive, and this is the answer. If I multiplied those two binomials back together, I would get 5n squared. 7 times 9 is 63. 7n plus a 9 times 5n, which is 45n, would give me 52n. Now that's going to feel like a lot the first time you look at it. If you look at my work, it may not make a lot of sense, but after you hear the explanation, it should start to click. Let's look at another one. On this one, I see a 9, I see a 36, and I recognize that a 9 goes into both of those numbers, or a 3. But 21 doesn't share one of those factors. So there is no greatest common factor, and I'm ready to start factoring this. Now look at your first term. It says 9n squared. 9 is not a prime number. We actually have a couple possibilities here. It could be 1n and 9n, but it could also be 3n and 3n. Typically, I start with this one. That doesn't mean that it is that setup. It's just from experiences. I typically have noticed that it's the numbers that are closer together rather than some extremes. Now, if this should say n on here. Now, if the middle term is a very large number, it might be the 1 and the 9 to help you get to those extreme values. I'm going to start down here with it. Let's look at the 20 at the back. There are ways to get a 20 through multiplication other than just say 4 and 5. The other way would be 10 and 2, or you could actually do 1 and 20. Now you might notice that this is a 3n and this is a 3n, which means I don't need to worry about checking both situations. If this is a 4 and this is a 5 and I flipped them around, because these are the same, I would still get the same products, and that doesn't change anything there. So since I see a plus sign, I'm using that to tell me that I need to add, and my signs will be the same. Add, and then the same signs. And if you know that the signs are the same, and you see a minus here, then I know it's going to be minus and minus. So if you want to go ahead and do that, you can go ahead and set that up. So let's see how we can achieve a 36 by adding these products together. So let's put a 4 here in our heads and a 5 here and start multiplying. That's a 12, and 5 and 3 is 15. And if we combine those, 12 and 15, is it 36? No. So it's not a 4, and it's not a 5. Let's try 10 and 2. Well, if that's a 10, that's a 2. Multiply here, you'll get 30. Multiply here, you'll get 6. And if I add those, I will get 36n, which is what I wanted. And so after just 2 tries, I found the correct values. It's important to understand that multiplying this back together would get me this expression here. And lastly, look through. Is there a greatest common factor? I do quickly notice that these are all divisible by 5. So I'm going to factor out a 5 from each term. Again, if you don't know how to factor out a greatest common factor, you can watch a video about that. But you're going to pull the greatest common factor out, and we're going to divide each of those 3 terms by 5. So it leaves us with a 10n squared plus a 3n, and then minus, that's 27. So the 5 will remain as part of my answer, and now I have a trinomial that I can factor like we did previously. 10n squared. There are 2 different ways that I can create 10n squared. One way would be 2n and 5n. The other way would be 10n and 1n. I really think it's going to be the 2n and the 5n. Another thing is the 27. Yes, there are a couple ways to make a 27 through multiplication of integers, but I think it's going to be 9 and 3. Typically, your math facts, the numbers that are closer together, again, not the extremes like 1 and 27, typically work for me. I'm not saying they always do, but it's a good place to start oftentimes. This time I did have to check both situations because we have a 5n and a 2n, and those will produce different products. So let's imagine right now that this is a 9 and that this is a 3. If I multiply here, I'm going to get 45n. And if I multiply here, I'll get 6n. Now this one is a minus, which is the first time we've seen that. And that does mean to subtract. The reason it's subtraction is because you are combining products that would have different signs. So you've heard the same signs you add, different signs subtract. That's kind of what's happening here. So if I subtract a 45 and a 6, I'm going to get a 39, which does not give me a 3. So it's not 9 and 3, at least in that order. So I'm going to try another set of numbers, or this set, and we'll go this way, 3 and 9. If I multiply here, I will get 15. If I multiply here, I will get 18. And if I subtract those, I will get 3. Now, depending on which one is negative and which one is positive, I can manipulate whether I want it to be a positive 3 or a negative 3. Since here, if I did 15 minus 18, that would be negative 3. I really want the negative to be on the 15 so that this will be positive, making a positive 3. So looking back at our multiplications, I want to make the 15 the negative. Since the 3 times the 5 is what made the 15, I'm going to put the negative here. I'm going to put the positive here. I have now found the factors, and I was able to realize that it was the 2n and the 5n, and it was the 3 and the 9. So I have to check all those combinations, and yes, that can take a while. But it really helps you with understanding the numbers, and it really helps you with understanding how factoring actually works. There are lots of other methods that can be used, but I don't feel that students really understand what they're doing when they use these gimmicky approaches. That being said, I'll probably make a video for those as well.